This is ATP molecule and this has three parts: adenine ring, ribose sugar and phosphate group, which is key here. If mitochondria is powerhouse of cell, this ATP molecule is the battery produced. In high school, we learned that ATP is generated by glucose breakdown, and breaking chemical bonds in ATP results in energy release. But isn't it odd that in this example, breaking bond releases energy, but generally bonds require energy to be broken? ATP is not an exception to this, and if this is how you are picturing energy release, then you are way off. At least I did. What I was missing for the visualization, it requires understanding energy in biological systems, entropy, and how it all ties back to the structure of ATP. Since you started watching this video, you have burned around 10 raised to the power 21 ATP molecules. How many billions is that? It's literally a trillion billions. And if you tap the like button, that tiny motion just cost your cells 2 to 3 trillion ATP molecules. As for making this video, let's just say my mitochondria has already spent more ATP than all the stars in our galaxy. And how many ATPs would you get from one glucose molecule? Only 32. Yeah. But here's even more crazy part. By the end of today, your body will use so much ATP that the total amount will be more than your own body weight. What? How can you burn more ATP than you even have? Because ATP is not a fuel. ATP is simply a rechargeable courier, a tiny molecular battery that gets charged, discharged, and charged again. What do you get from glucose? Electromagnetic potential. Electromagnetic potential stored in the bonds of glucose molecules. So before we go any further, let's pause and visualize what energy actually is. Only then does the rest of the story make sense. Energy is the capacity to do work, but that's not a picture. It tells you what energy does, not what energy is. So where exactly is the energy in this molecule? It sounds like a stupid question, but it's actually one of the hardest to answer. To visualize energy, at least some forms of it, it helps to think of energy as motion. Whenever matter moves, vibrates, rotates, wiggles, stretches, or compresses, we call that energy. Temperature and heat, just molecular motion. And when there's potential for motion, we call it potential energy. At the electron level, something different happens. Higher energy means larger, more spread out electron waves. So for electrons, energy isn't just about motion. It's about arrangement in space, where an electron sits relative to nucleus, which determines its potential energy. Electrons are confined to orbitals, and this spatial arrangement constantly creates potential energy. So one of the keys is how much potential energy can ATP concentrate in electronic bonds. And to know about this concentrating ability, we need to understand the diffusion of energy first. All systems naturally move towards lower potential energy. But when potential energy is released, it doesn't become one simple motion. It spreads. It diffuses across many possible movements called degrees of freedom. And the process of spreading is called entropy. Degrees of freedom include translational motion, rotational motion, vibrational motion, electronic orbital changes, and even nuclear energy. This is also a hierarchy of energy density. Nuclear energy is vastly more concentrated than electronic energy, which is more concentrated than vibrational, and so on down the chain. The more concentrated the energy, the more useful it is for doing work. Consider two molecules with the same total energy. One has 5 degrees of freedom, the other has 10. The molecule with 10 degrees of freedom spreads its energy across more motions, each motion holding less energy, less concentrated, less able to drive work. More degrees of freedom means more dilution, means less usable energy. This is the universe's energy waterfall. Energy naturally flows from concentrated to diffuse, nuclear to light to chemical to heat. Everything in physics pushes energy towards diffusion and uselessness. Yet life needs the exact opposite: highly concentrated, highly usable energy. The question becomes, how do you concentrate energy and keep it that way? To answer that, we first need to understand what makes energy usable in the first place. It's not enough to have energy. Energy is only useful when there is a gradient, a difference between two states, a reservoir above a valley, a hot region next to a cold one. All work happens when energy flows from high to low. No gradient, no flow. No flow, no work. But here's the problem: entropy naturally erases gradients. Energy spreads out, differences disappear, and what's left becomes useless for doing anything. So, life faces a fundamental challenge. It needs to do the opposite of what the universe wants. It needs a molecule that can concentrate energy, hold it against tide of entropy, and release it precisely when needed. That molecule is ATP. So, how does ATP actually do this? This is a phosphorus atom. The valence electrons of both atoms are in p orbitals. The electrons are in search of a pair to get stabilized. Thus, this phosphorus has three unpaired electrons. In ATP molecules, this phosphorus bonds with four oxygen atoms, and this leads to very high electrostatic tension. In this picture, the red color of the bonds represents how powerful the electron repulsion is. So all this potential energy is stored in the molecules of ATP. But when ATP splits into ADP and inorganic phosphate, at that very moment, resonance stabilization and orbital rehybridization occurs. This allows electrons to delocalize across more space and thus access more microstates. This lowers the electrostatic potential energy of the system. This is a graph of Gibbs free energy. On the left side are reactants, on the right side are products, and in the middle is the transitional state. On the y-axis is plotted the free energy of the system. ATP has high free energy because of high electrostatic potential. ADP and inorganic phosphate has lower free energy because of resonance stabilization, which increases entropy and accessible microstates. This peak is the activation energy. That is what makes the ATP molecule kinetically stable. This is what it actually means when we say ATP releases energy. Energy isn't released into thin air. The difference between high and low potential energy becomes electromagnetic force. Charges rearranging, repulsion shifting, pushing directly on protein atoms. That precise push, that's actually the work, not some abstract energy floating around. Actual forces moving atoms, changing shape, that drop from confined to spread doesn't release energy. It redirects electromagnetic repulsion into mechanical force. This actually shifted my perspective on energy. When we say energy is released, we really are accounting all of these conformational chains through a bookkeeping system of motion and potential of motion.